Integration by substitution here?
Yeah.
Okay. If they've told you the substitution, then we just take them literally, don't we? And
Yeah.
start by saying, let's find a few things that fall out of that. Almost certainly, well, we might like to have sine x somewhere along the line. So yes, let's get, when we see the sine x there, we think, let's get sine x in terms of u. Yes, how would you set about getting sine x in terms of u?
Sine x. I'm not sure about sine x actually.
Well, let's get cos x in terms of u.
Cos x. So cos x could be u take away 1.
Yeah. And what's sine in terms of cos?
Sine is.
I mean, if the angle there is x,
Yeah.
let's call it theta.
Opposite.
No, let's call it x. There and if the hypotenuse is 1,
yeah,
the opposite side is what in terms of x? If the hypotenuse is 1,
is it a half?
not necessarily. Depends what x is, doesn't it?
Yeah.
I mean, you're right. X does look like 30 degrees, and the opposite side would be a half. But I'm talking about any angle at all. We could say the opposite side was, well, opposite over hypotenuse, of course. What do we call it?
Yeah.
Sokotoa tells us to call opposite over hypotenuse what?
Sine x.
Yeah. So if it's over 1, the opposite just is sine x.
Yeah.
And the adjacent just is?
Is it cos x?
Yeah. Because it's adjacent over hypotenuse. So if the hypotenuse is 1, let's assume, the adjacent side is cos. Now, can you use Pythagoras to tell me what sine x is in terms of cos?
Sine x in terms of cos.
Pythagoras.
Oh, is it 1 take away cos squared?
Well, what would be 1 take away cos squared? Not quite sine, but
Sine squared.
yeah. So sine itself is
1. No, root 1 take away cos squared.
Yeah. Which, if we use that, we can turn into what?
Root of u squared take away 1 squared.
There's more to it than that, isn't there? It might come out like that. Apologies if so. But I want you to think this first of all. Does it come out like, well, what did you say? 1 take away u squared?
Yeah,
Not
I
quite,
said
no.
you take away 1 squared.
No.
U squared take away 1 squared.
No,
okay.
it's not quite, is it? We need to expand that, don't we?
Yeah.
So we have got the square of cos is the square of u minus 1.
Yeah.
So then when we expand it, what have we got?
Got u squared take away 2u.
Yeah.
1.
Plus 1.
And
so when we remove the brackets, what have we got? We've got 1 minus what?
we got 1 minus u squared minus 2u plus
Careful
1.
though, if we're removing the brackets, we want to cancel the minus 2u, don't we? We want to cancel the minus in the 2u. We're taking away minus 2u.
Oh, so it's plus 2u. And then take away 1.
Take away 1. Yeah. Which simplifies to?
U squared plus 2u.
No.
Don't the ones cancel out?
Yes. Leaving?
Oh, minus u squared plus 2u.
Yeah. 2u minus u squared. Good. So we have got an expression for sine.
Yeah.
Now notice what I did there. When we were about here, I thought, oh God, did we have to do this? You know, I just suggested it as something that might be useful. I'm not certain that we need it because it might fall out of course it will. When we do the other thing that we usually do. So the point is, what I've just demonstrated is that you don't necessarily have a plan, and you might change your plans. But one thing you can depend on, and perhaps I should have done first, was say, what's du dx? Almost depend on that. It's going to be worth doing.
Wait, du dx of what? The cos x equals u minus 1.
No, good point. If we were here, what does this mean?
Yeah.
It could mean things, but if we go back to here.
Okay. Oh, okay. So we would get minus sine x.
Yeah.
Plus 1? No.
No, just minus sine x.
Minus sine x, yeah.
But then that'll account for the sine x here anyway.
Yeah.
So we didn't need all that. What else have we got? What about dx? We might want to substitute for that. And indeed, what we found here really is a substitute for sine would be du over dx, and then you can think of sort of cancelling the dx's.
Yeah.
I've changed tack a few times here now, haven't I? Probably not inspiring confidence, but make dx the subject of that. I know we try not to think of du dx as a fraction often, but when you're doing substitutions, yes, you do think of, suppose that means du divided by dx, then what does dx equal?
Is it du over minus du over sine x?
Yeah, yeah. So let's call it minus du cosec x, or times 1 over sine x. Or I could have put it over sine x, but I would rather keep that as a, so I can put it on the end. In fact,
yeah.
I would rather have done it like this, look. Yeah. So we can replace du dx with all of that.
Yeah.
And then everything's taken care of, isn't it? Oh, except for, okay. So what you can do is absolutely strictly say the top there means x value of pi over 2, doesn't it? Because this was with respect to x. So the pi over 2 there was an x value. The 0 here was an x value. And then we had e to the cos x plus 1, but we know we're going to be able to replace that with
u minus 1. Right. Yeah, u minus 1 plus 1.
Well, cos x plus 1 is just u.
Oh, yeah, yeah.
Oh, I see. Yes, we could replace the cos x there with u minus 1 and then add 1.
Yeah. Yeah.
So we're back at u. Sure. The sine x, I did think about replacing that, but I've changed my mind. But what we are going to replace is the dx. So just absolutely, when you're given a substitution, take it literally as much as you can. In fact, you know, perhaps we should put that there for sine x.
Yeah.
Except that then we've got a sine x here. So we should put that there as well, and then they'll cancel. So the sine x's are going to cancel, and it doesn't matter whether you're cancelling sine x or the equivalent root of 2u minus u squared. So this adventure here, you can use it if you want to say, I want to replace absolutely everything in here. P is a constant, that doesn't need replacing, but every mention of x in here, including the implicit mentions of x at the limits here, I want to replace with something to do with u. So we could do that. In fact, let's be absolutely dogmatic about it. Yeah. Let's replace each one of those 1, 2, 3, 4, 5 bits with what we've established. Oh, we haven't done this conversion. X equals pi over 2 is going to give us a u value of
x equals pi over 2.
So what time on the clock is pi over 2?
12.
Yes. And what's the cos of 12 o'clock? Cos is which axis, vertical or horizontal?
Is it horizontal?
Yes. So the cos value of 12 o'clock is?
The cos value of 12 o'clock is...
In other words, the horizontal coordinate of 12 o'clock.
Is it 90 degrees? No, wait.
Pi over 2 is 90 degrees, which is 12 o'clock on the clock, isn't it?
Yeah, yeah.
How do you find the cos of any angle? You think about the...
adjacent over hypotenuse.
Yeah, but you don't, in general, you know, that's only going to work for real triangles. You can't really have a right angle triangle, one of whose other angles is 90. So you have to start thinking about the unit circle, don't you? And think,
Yeah.
okay, I'll just regard cos as being the horizontal coordinate of any point on the circle.
Yeah.
And what's the horizontal coordinate of the 12 o'clock point? Assuming that the origin of the grid is at the center of the clock face.
I'm not sure.
Think of a clock face.
Yeah.
And think of two axes going through the center of it.
Yeah.
The cos of any angle is the horizontal coordinate, the cos coordinate,
Yeah.
the corresponding point on the clock face.
Okay,
Well,
so
think of that point.
At 12 o'clock, would it be 0?
Yes. Horizontally, that's 0, isn't it?
Yeah.
Vertically, what is it?
1.
Yes. So sine of pi over 2 is?
Sine of pi over 2 is
The vertical coordinate.
1.
Which is 1. Cos of pi over 2 is? The horizontal.
0.
0, because it's the horizontal coordinate.
Yeah.
Okay, that's what you've got to go through all that if you're going to really get on top of trigonometry, even if you're doing it different ways at other times. I do want you to learn that. Okay, so cos of pi over 2 is?
0.
Yeah, I don't mind drawing the picture as well. I just thought on this occasion. Let's talk about it so that I know you're looking at a picture in your mind's eye. Pi over 2 is at the top of the clock. Isn't it? So horizontal axis gives you the what values? What's this axis telling you?
Oh, that's cos.
The cos values of all the angles on the clock. And the vertical axis is giving you
sine.
The sine values of all the times on the clock. So for pi over 2, which is 12 o'clock, cos is
0.
Yeah, because that point there has got coordinates of 0, 1.
1.
Cos and sine are 0 and 1.
Yeah.
So u would be what for an x value of pi over 2?
U would be, is it 0?
What are you thinking when I say u?
Cos x.
You're thinking cos x when I say u?
Yeah. So wait.
What if they told you to think for u?
U is cos x plus 1, so it'd be 0 plus 1.
Yeah.
So it means it's 1.
Yeah.
Oh, okay, yeah.
So that gives us something to replace that with. Instead of thinking a limit of x equals pi over 2, we can say a limit of u equals 1.
Yeah.
And when x equals 0, u equals what?
When x equals 0, u equals, is it 2?
Yeah. Okay.
Yep.
So now let's, we've prepared the ground completely, haven't we? Let's replace absolutely each and every component.
Yeah, so we have...
So the upper limit will be
1.
Yeah.
Yeah.
Which is the u value of 1. I mean, if you want to be quite clear, there's no harm. Nobody will mind. Quite the opposite. If you put u equals 1 there.
Don't you normally have the large number at the top?
Good point. Yes. Okay, but we'll do that in a second.
Okay.
That is true. But we can. You don't have to either. We usually do. So we'll just leave it for the next line. But we can say this integral exactly equals this integral of e to the what?
E to we got was it u minus 1?
What? Cos x
no,
plus 1?
No, cos x plus 1 is it's u.
It's just u.
Yeah.
What was sine x, did we say, in terms of u?
Was it sine x? Oh, what do we think that was? Didn't we say it was?
We got an expression for sine x in terms of u, didn't we? Can you see where?
Yeah, it's the root.
Yeah.
2u minus u squared.
Yeah.
Oh, yeah, we said. Oh, I thought we said we weren't going to use that. Oh, but yeah.
And then I said, I'm not going to bother using it. You'll see why in a second. Why I prevaricated there. So that's sine.
Oh,
and now dx.
Yeah.
What did we say?
Minus sine x.
Yeah. Times minus 1 over sine x, or we could now write that, couldn't we?
Yeah.
times
du.
du. Now we'll simplify a bit. What's the relationship between that integral and this one?
Wait, what do you mean?
Well, if I change the 1 and the 2 there,
Yeah,
to go from 1 to 2 instead of 2 back down to 1,
yeah.
what's the effect of that?
We'll get a positive outcome at the end instead of a negative.
Yes. In other words, these are the negative of each other.
Yeah.
So if I swap these numbers round, I really want to put a minus sign before the integral. Right?
Yeah, yeah,
But I know that's going to cancel with this one here, don't I?
yeah,
So I'll just drop that and also drop this one here.
yeah.
So now what we've got is e to the u what?
E to the u. Well, wouldn't it be e to the 2? Well, are we substituting it?
No.
Okay, so
No, this is a variable. These are particular values of u, but this is u, a variable.
okay, so is it one? Is it minus 2u minus u squared? No, minus 2u plus u squared, and then take away 1.
We've cancelled the minus sign there.
Okay.
We're multiplying by that root, and then we're multiplying by 1 over that root.
Okay, yeah.
So,
oh, we just get that root. We just get 1.
Yes. So they just cancel.
They cancel each other, yeah.
Leaving?
Is it 1? Or is it? Yeah, is it 1 or minus 1?
The minus cancelled with the switching the limits, didn't it?
Yeah. So then it's just 1.
So if you switch the limits, it's just times 1. Well, that doesn't need saying, does it?
Yeah. No.
That goes without saying.
And then so it'd just be EU du.
Yeah. Which equals? So notice, you know, when I said, oh, why did I bother doing that when I could have just had sign here?
Yeah, is it because it cancels out?
Yeah. So whether it cancels with that sign or whether it cancels with 1 over that version of sign.
Yeah.
So that can be a bit off-putting. You know, it made me seem aimless, didn't it?
Yeah.
And prevaricating. And it can be off-putting when you're doing it. Oh, do I need to substitute for this or that? Well, if in doubt, be absolutely strict with everything. And when you've differentiated u with respect to x, and you've got another mention of x, try and replace that as well with that.
Yeah.
And do what we did here. Although it is overkill because the signs would have cancelled anyway. The sign x's would have cancelled. So let's do the quick version. Well, except that it's not really the quick version. You know, the whole thing is overkill. Using the substitution, I mean, why?
Yeah.
You should do that by inspection, really. That's not a good example of a u substitution because it's completely pointless. You should look at that and think, oh, there's a product where I can recognize that one part of the product is the derivative of the inner function of the other, which is a composite.
Yeah.
You remember all of that kind of palaver, yeah?
Yeah.
But it's much quicker to do it by inspection. Having to go through the u substitution and not get lost is a trial in itself, but they're giving you 6 marks for it, so fair enough to see if you can negotiate it. Right. But the quick u substitution way would be as follows. Here's how people would do it. If you're looking at that thinking, well, that seemed a bit complicated. But we're saying starting with from 0 to pi over 2 of e to the cos x plus 1 sine x dx, people would go as follows. Okay, from x to u, pi over 2 to what value?
Was it? It was 1,
And from 0 to
2.
2. And since du dx is what?
Du dx was, what was it? Was it minus sine x?
Well, yeah, I mean, think it through then. Don't just try and remember, but it is minus sine x. Think of why that's, because you're differentiating that, aren't you?
Yeah.
With respect
Yeah.
to
So, yeah, it would be
okay.
minus. Yeah.
So minus sine x, and therefore dx equals. If you're doing a u substitution, you do need to do that. You do need to replace dx with du.
Yeah.
But, and that can be confusing without practice. You think, okay, so what's du? And you're trying to get an expression for du. So unless you've had enough practice, that can lead into the doldrums. But if you're aware that you're generally going to be replacing dx, and dx is what?
It was minus 1 over sine x,
Yeah,
times du.
and in fact, you know, you can do that.
Yeah, du over
The
sine.
way you said it, as long as you're clear on the dangers, the potential confusions. So you go from there to precisely right, and yes, you would be going from 2 up to 1. Probably do save that as a separate step. Then you're saying e to the u sine x, and then times minus du over sine x. Cancel the signs, and then cancel that minus by flipping the limits. Okay, so that's the slightly shorter story.
Yeah.
Not much shorter. Okay, so, you know, don't be afraid of being meticulous in, you know, substituting for anything at all that mentions x or refers to x implicitly, like the limits there. Okay, so that's going to be what?
So so how would you get a value for du? So I know you'd swap you'd be e to the power e squared, but then what happens to du?
You just forgotten the your basic integrals, have you? What's the integral of e to the u?
That's e squared, isn't it?
No.
We're integrating. Oh wait, sorry. I mean, that was.
No, I think you're still thinking. I don't know what you're about to say. Of course, go on, say it.
No, Linux. Oh, is it u to the u e to the power u?
No, that's a more complicated case. This is as simple as it gets now. Now that we've done a substitution, we don't have to think about the chain rule. I would rather have done this using the chain rule.
Okay.
I think I will before we move on, if you don't mind. Just doing it as by inspection, a backwards chain rule thinking process. Right, 5 different basic results. A x to the power of n differentiates to what?
Oh wait, what?
Where n is any
So it'd
constant.
be a.
So
It would be
it's where
a n x n minus 1.
Good. Sine.
Cos
Cos.
minus sine.
E.
E.
Yeah,
uh,
that's all.
Okay.
Finally, log.
Log 1 over x.
Right. You were starting to do this, weren't you?
Yeah.
For
Yeah.
this. It's just that.
Yeah. Oh, okay.
Okay, so inside the square bracket, enclosing antiderivative or indefinite integral.
So it's e squared.
Oh, what's going on? Are you down here again?
E to the u. So are we substituting 2 with u?
Bear in mind, I didn't put an x here. Could have been
Yeah.
theta, could have been u, could
Yeah.
have been x, could be anything.
So is it just still e to the u?
Yeah.
Oh no, I thought you were using the integrals, and I was like substituting the 2 in and the 1. So I thought the u would become a 2.
Oh, all right. Oh,
Yeah,
okay, I'll get off
yeah.
your case. Well, except that, what on earth did you think I was writing here with that big square bracket?
Yeah, I
Don't
thought.
you do this stage? Don't
Yeah,
you put the
so I thought the u.
antiderivative in there,
Yeah,
and then the limit's there.
yeah.
Okay. All right. Now I get you. You were just going from here straight over to here, which is
Yeah.
what?
E squared.
Yeah.
Yeah.
Minus.
And minus e.
Yeah. Okay. And that is where we were meant to get to. I think they factorized, didn't they? They took e out.
Yeah.
And inside?
Was it e minus 1?
Yeah. Oh, okay. All right. Anyway, does no harm to remind ourselves that's all we need, plus what rules of combination for differentiating?
What rules?
Because, I mean, if things are combined as one thing plus another,
Yeah.
the derivative of all of that would just be that, wouldn't it?
Yeah.
But of course, things aren't only combined with adding or taking, they're also combined with,
Multiplying.
sorry?
Multiplying.
Yes, in which case you would need to apply.
Is it the chain rule?
The product rule and the
Oh,
chain
the
rule
product.
for composites,
Yeah.
which is another way we combine functions, isn't it? By composing them,
Yeah.
having one followed by the other, or one outside another. Right, so there we are. Here's what I would have done, and you should do too as well. If you're not told specifically to do a substitution, how should you do this integral? You definitely should think like this. Okay, so opening bracket, closing bracket. What we're talking about is the integral of that stuff inside. So what we want is whatever it is that differentiates to give that stuff inside.
Yeah.
And then we should see that, oh, we know what's going on here. E to
Yeah.
the blob is multiplied by something that looks suspiciously like the inner function of the thing inside. But it's not quite. Let's test it. So we think it's e to the blob.
Yeah.
So, we need the chain rule. E to the blob differentiates to e to the blob times the derivative of the inner function, which is what? What's the derivative of cos x?
Minus sin x.
Minus sin x. So we do need a minus sign there, but in that case,
Sin x. Wait,
is the equal sign still okay?
yeah.
No, not now. We've got a minus sign there.
Oh, it's not equal to.
How can we make this equal sign true again?
Is it by putting it in the brackets and timesing it by -1?
Yeah, I mean, because this is a product, I don't really need brackets there. If you mean
Yeah.
minus sign,
Yeah,
true.
Yeah.
In which case? The equal sign is okay now, but what's not okay?
Is it the minus e cos x plus 1?
Up here, yes.
Yeah.
If that's what you meant, or were you talking about down here?
I was talking about down there.
Yeah. Well, the point is, the equal sign is okay now, but until I put a minus here, the differentiation isn't okay.
Yeah.
Now the differentiation's okay. Look, we'll check it. Minus e to the stuff is going to be minus e to the stuff because the minus just comes along as a multiple. And then the inner function differentiates to minus sine x. Everything's cool. The minuses cancel. We've got what we were trying to integrate.
Yeah.
But what's this about? This is a bit different to what we did before. But hopefully it'll give us the same result. Let's find out. Okay, you ready?
Yeah.
So what's minus e to the power of cos of pi over 2 plus 1? Well, what's cos of pi over 2?
Cos of pi over 2 was that. That was 1. No, that was 0. That was 0.
Vertical coordinate. Sorry, horizontal coordinate, wasn't it?
Yeah, 0.
Notice. You've got to think, cos is horizontal. Literally, think it through. For 12 o'clock, that's a horizontal coordinate of 0.
Yeah.
So cos x plus 1 is?
1.
So we've got minus e to the power of?
1.
1. Followed by? We minus whatever we get from putting 0 in here, which is what?
Cos x equals 1, so 1 plus 1, 2. So minus e to the 2.
Cos of 0 is 1, so 2. So we've got minus e
to the 2.
To the 2, which of course simplifies to?
E take away, minus e plus e squared, which could be written as e squared take away
minus e.
Yeah.
So same again. Okay, so notice how it was all unnecessary, but it's meant to be a mechanical process for helping people who don't understand this by inspection. And then for more complicated cases, yes, of course, it is useful in its own right. But in this case, it was overkill, because we might as well have done this, which with practice, you will do by inspection, as the phrase suggests. You just inspect it and think, oh, yes, I see what's going on there. We get this. Okay. But what is meant to help become, as so often in maths, something that was meant to make things easier becomes a trial in itself, which you have to be tested on, mastering. It's a matter of taste. Some people love a U substitution. Some of those people even understand how it's codifying what we're doing there.
Yeah.
In the end, what you've got is an integral with that result, which comes of, you know, subtracting this result from that result. But a substitution can help.
Yeah.
Or hinder, depending on how you look at it. But the integral is basically a process of working backwards through the chain rule.
Yeah.
Even if you end up preferring a U substitution over this kind of logic, do be aware that that's the logic behind it, working backwards through the chain rule. Okay?